Good. So yeah, this is a probably unusual time to start the PMIP wing seminars, but I don't expect any Europeans can join because it's midnight, but hopefully some Asian time zone people can join and some American time zone people can join. I think I will wait another 1 minute or so because we're still having increasing number of people. Okay, then I would like to start the 10th PMIP Wing seminar. We have a rather small group, but hopefully we can discuss intensively. And the first speaker is Gabriel Pontes. He's a research scientist at the Climate Change Research Center and the Australia Center for Excellence in Antarctic Sciences at the University of South Wales. We'll talk about ENSO sensitivity to background states, lessons from multi-climate analysis. Please, Gabriel.
Great. So thank you, Masakazu, for the introduction. And I also want to thank the PMIP Wings Organizing Committee for inviting me to present my work at this seminar. And today I'm going to explore the ENSO sensitivity or the sensitivity of the El Niño Southern Oscillation to background states. And I'll present some results from remote climate analysis. So the main goal of this remote climate analysis is to try to extract the most out of the wide range of climate states that has been simulated within the PMIP project. And we know that those different climate states, they apply different boundary conditions and different climate forces that can affect ENSO activity. So within this work, I also want to thank people that have contributed to it, and these include colleagues from the Pleistocene Model Intercomparison Project, from the University of New South Wales, and from the University of São Paulo. So I'm going to start with a quick introduction of the background of the tropical Pacific mean state and try to describe a little bit the main features of this tropical Pacific state. And we know that in the tropical Pacific, we've got very strong trade winds reaching the Western Pacific, and those trade winds, they push those warm water, those surface warm water westwards, and also driving the zonal Walker circulation, and also change in the oceanic mean state with a steep thermocline slope between the Eastern and the Western Pacific. And what we can see from the literature is that there are a number of processes, those from the tropical Pacific mean state, that have been suggested to be controlling ENSO activity. So one of the most cited process is the zonal SST gradient between the Eastern and the Western Pacific, which has been suggested to be controlling ENSO activity in both paleoclimate and future warming. We also have got the thermocline depth, so the depth of the thermocline, the mean thermocline in the equatorial Pacific. More recently, ocean stratification has been posed as the most important process affecting the enhanced ENSO variability under the global warming. And from an atmospheric perspective, winds in the equatorial Pacific are very important. So the intensity of the winds, and not only the zonal winds, but also the meridional winds across the equator. And here, more related to the mid-Holocene climate, we know that one of the major forcings of the mid-Holocene was the enhanced solar radiation in the northern hemisphere. But a study has also found that the feedback with vegetation could also affect ENSO activity. And more recently, we found that the position of the Pacific intertropical convergence zone has been the main process behind the suppressed ENSO activity during the mid-Pliocene. And I'm going to explore a little bit more this study, and then we are going to move towards the multi-climate analysis. So first, a quick introduction of the mid-Pliocene warm period that occurred about 3.2 million years ago. So one of the major climate forces for this period was the reduced polar ice extent. So both Greenland and Antarctica ice sheets were reduced, and the CO2 concentration was at about 400 ppm. And if we ask models to simulate those climate conditions for the mid-Pliocene warm period, where the main response is the polar amplified warming with enhanced or greater temperatures found at the polar regions of both hemispheres. Yeah. And if we explore the tropical variability within the PMIP ensemble, what we can see is that there is a general reduced variability over the tropical basins of the global tropical basins, but this is more intense in the equatorial Pacific, as we can see from the top panel, which is showing the change in the amplitude of the standard deviation of the sea surface temperature.
Sorry, Gabriel, are
yeah.
you forwarding the slide? I only see the cover page, the first page.
So you are still in the first page? So
Yes.
can you see it now? Or?
I can see now, yeah. But I think the forwarding the pages didn't seem to work.
Okay, so I'll just try to share it again.
Yeah, sorry.
No worries, that's all right. Just a moment. It's not allowing me to share this, so no, that's not what I want. Can you see it now?
Yes, thank you.
Perfect. Thank you. So yeah, also as I was saying, so the top panel is showing the change in the SST variability across all of the tropical basins, and we can see that this signal is much more stronger in the equatorial Pacific. And if we pick the Niño Tree region, which is one of the key regions that have been suggested for evaluating ENSO activity, we can see that most of the models that is basically near unanimous ENSO weakening across the PLIOMIP models. And then now we are going to explore or investigate a little more the causes behind this unanimous weakening across the PLIOMIP models. And we started by investigating the change in the sorry, Masako, can you just confirm that you are seeing my slide?
Yes, I do.
Perfect. So, and we were going to start investigating those processes by looking at the oceanic features that could possibly have an effect over ENSO activity. And what we found was that although we can find some significant correlations between the change in the ENSO activity and both the thermocline slope of the equatorial Pacific and the ocean stratification, we found that those changes cannot fully explain the ENSO weakening across the PMIP ensemble. So for both of them, what we can see is that half of the models are showing a change in one direction, and the other half of the models are changing the other direction. For example, here for the thermocline slope, we basically have half of the models indicating a change towards a La Nina-like mean state, which would be associated with a steeper mean thermocline. And the other half of the models indicating change towards a La Nina-like mean state would be associated with a flatter mean thermocline. And the same can be found for the ocean stratification. So then we moved into investigating process related to the atmospheric dynamics. And with respect to the atmospheric dynamic, we found a high model agreement suggesting enough water shift of the ITCZ. As you can see here on this figure, it is showing increased precipitation in the tropical northern hemisphere and decreased precipitation in the tropical southern hemisphere. So they suggest a northward shift of the ITCZ. And if we take this shift within the tropical Pacific and correlate that with ENSO, we found that this can basically explain this reduced ENSO activity for most of the PMIP models. And what this relationship is telling us is that the further north the ITCZ shifts, the greater is the reduced ENSO activity. And we can see that most of the PMIP models suggest a northward shift of the ITCZ together with this reduced ENSO activity. So let's explore now how this northward shift of the ITCZ can change the tropical Pacific mean state in order to reduce the ENSO activity. So basically, the northward ITCZ shift in the mid-Pliocene was a result of higher rates of warming in the northern hemisphere than the southern hemisphere. This is more associated with enhanced polar amplified warming in the northern hemisphere. And this also drives changes in the meridional and horizontal circulation. So this results in an intensified southern hemisphere hadron circulation that also intensifies the subtropical high system and winds, generating intensified winds in the western equatorial Pacific. And those intensified winds in the western equatorial Pacific, they are very important because they are going to suppress processes that are important for triggering ENSO activity. So it's basically suppress the variability of the winds in the Western Pacific, and thus reducing the chance of the development of El Niño events. So now, one question that raises from this work is if this framework that has been successful for the mid-Pliocene, it can be applied to other climate periods or climate projections. And here, so we were investigating basically the mid-Pliocene, which has occurred about 3.2 million years ago with a mean warming between 2 and 4 degrees. But we also have other target periods, other warm climates that have been object of study of the PMIP of the PMIP project. And here we've got two of them, which are the last interglacial with a warming between 1 and 1.5 degrees, and the mid-Holocene, which has experienced a less significant warming, but it's still important in trying to evaluate those changes in the background state. And for completeness, I will also include here the high emission scenario until the end of the 21st century. And if we start to compare the mean state of the tropical Pacific in those simulations, what we can see is that most, or basically all of those past warm climates, including the mid-Pliocene, the mid-Holocene, and the last interglacial, they share similar changes in the equatorial Pacific mean state. So they all suggest an intensified subtropical high system in the southern hemisphere with intensified winds in the western Pacific and a northward shift of the ITCZ as suggested by a warming in the northern extratropics. And this is all related with a reduced ENSO activity in those 3 recent past warm periods. But if we move towards the towards the future simulations, we can see that these future simulations are suggesting an opposite response. So, and this is an enhanced equatorial warming with reduced trade winds and enhanced ENSO activity as well. So basically, the analysis of the mean state and the ENSO activity is suggesting that in those different scenarios, is suggesting that the future increasing ENSO activity has likely no past analogy. So it's likely unprecedented in those past 3 million years. And so here, what we want to do is we want to include in these analysis, in this multi-climate framework, we want to include as many scenarios as possible. And I'm going to use more than 170 simulations. We also can account for ENSO complexity, because before we were analyzing ENSO as just a single index, which was the linear tree index, but we can also account for the different types of ENSO, which are the Central and Eastern Pacific. And we can also account, and this is going to be necessary, especially for the future warming, for the different shifts in the ITCZ, but also in the subtropical Pacific convergence zone. So in the SPCZ as well. So you are going to account this shift in the tropical Pacific convection centers as an absolute shift. So we are going to take into account both the change in the position in the ITCZ and in the ICPCZ. And if we do that, that's the relationship that arises from the displacement of the convection centers, which now is going to be either poleward or equatorward. So if both the ITCZ and the SPCZ are moving equatorward, or they are moving far away from the equator, they are moving towards the poles. And the changing in some activity. So if we include all of these scenarios, which this analysis is suggesting is that the ENSO sensitivity to the climate states, it's a non-linear sensitivity. And most or all of the previous study, they have usually focused on a single climate state, in a single climate change scenario. And these give us the apparent, let's say, this give and what those studies found is that the ENSO sensitivity is basically linear within the climate state, as it was found for the mid-Pleistocene and as it was found for the future warming. But including all of these, we can see that there is a wide range of climate states that results in a non-linear sensitivity of the El Niño Southern Oscillation. And here I'm including all of the models, all of the PMIP and CMIP models. But we know that that some models, they cannot actually, they are not able to accurately simulate some process and some feedbacks that are important for ENSO development. So if we select only the models that best simulate the necessary process to accurately simulate the ENSO cycle, that's the relationship that arises from those. So it's a much clearer relationship, a much clear non-linear relationship if you select the best models that we've got at the moment. And here we can clearly see that most of the paleoclimate, most of those past warm climates, they lie on this part of the graph. And then we've got a slightly higher sensitivity of the El Niño for the high emission scenario. And if we go to further warming, although there is an increase in the ENSO activity, it then starts to decrease as the convection centers, as the ITCZ and the SPCZ are going to move towards the equator. And exploring the mechanisms of this sensitivity, we also found that the position of the tropical Pacific convection centers, they also modulate the ocean atmospheric coupling. And here I'm measuring the ocean atmospheric coupling by this coefficient, which measures the effectiveness by which wind anomalies are able to produce changes in the thermocline. So, and this again indicates that there is a non-linear relationship by which the convection centers can modulate the effectiveness of this ocean atmospheric coupling. So here, using this multi-climate framework, we can try to give a first step towards a unifying theory of the impact of the background state on ENSO activity. What we can see, one of the main results of this analysis is that if the convection centers, they move polewards, so they move away from the equator, it generates a more intense trade winds in the Western Pacific and thus suppress the variability of the ENSO, of possible ENSO triggers. But if those convection centers, they slightly move towards the equator, they slightly reduce the intensity of those winds and allow wind anomalies to develop in the equatorial Pacific. But if you have a full shift of those convection centers at the equator, these would vanish and they would suppress any variability within the equatorial Pacific, because those convection centers, they require that the zonal wind or the horizontal wind to vanish at the centers. So they would not allow the development of any wind anomaly that could be that could generate an El Nino event. And here I'm going to finalize with a few conclusions of this presentation. So the first is that the future ENSO increase is likely unprecedented in the past 3.3 million years, as indicated by those past warm climates. By using a wide range of climate states, we found that, in fact, the sensitivity of ENSO to those climate states, it's non-linear. And also that this sensitivity, that ENSO activity is likely tied to the dynamical changes rather than the thermodynamical ones, because it's not dependent on the degree of warming, but it's more dependent on the type of warming. And here I hope I could show you some of the usefulness of not only using a multi-climate analysis, but not only using a multi-model, but also a multi-climate analysis to evaluate the sensitivity of process and features within the climate system. So I will leave you here with some of the works that has been discussed in this talk, and I'd like to thank your patience, and I'm happy to take any questions. Thank you.
Thank you very much. It's very interesting, I found. Your slide didn't show up in the first or second slide. Do you want to touch upon slides in the first and second slide a little bit? Or...
So was this one that didn't show it up?
I think the first slide and second slide, I think. If we want to, if there are, I think the first three slides, yeah, those, if you want to add something important that.
Yeah, so basically those three slides, I was basically introducing some concepts related to the tropical Pacific mean state that are important for ENSO, and then suggesting some, and then discussing some process that have been suggested to be controlling ENSO activity in the tropical Pacific mean state. And I then started to introduce the mid-Pliocene climate, where one of the major forces is the reduced polar ice in both hemispheres.
Okay, thank you. So then I would like to move to questions and from the audience. We now have 20 people, so it's good. If I don't notice the hands up, you can just speak up. I have a question. What determines the difference between the mid-Pliocene response and the future response of the SSC patterns? That in the mid-Pliocene response, you show the meridian shift of the warming pattern of SST, whereas the for the future it's more east-west contrast of the SST pattern changes. What boundary condition do you think it makes a difference between the mid-Pliocene and future?
So basically, we have two main differences between those two simulations. One of them is the reduced extent of the ice sheet in the mid-Pliocene that caused a much higher polar amplified warming, and thus this has an impact in the energy budget in the atmosphere and driving those changes in the atmospheric circulation. And another difference is the CO2 levels, because although the mid-Pliocene can be considered a high CO2 level climate at about 400 ppm, it's still much less than the projected for the end of the for the 21st century under high emissions. And the CO2 effect on the tropical climate, it tends to amplify this warming at the in the equatorial regions. So that's why in the high emission scenarios, we can see that this more east to west increase in the sea surface temperature.
Yeah, what I found it's a bit yeah, what I'm saying that the in the future there is also a Arctic amplification, which means the larger warming in the northern hemisphere than the southern hemisphere. So you still have a meridional temperature contrast between the north and south. So I'm wondering why so you think it's not enough to shift the IDCZ to the extent that we have seen in the mid-Pliocene?
Yeah, it could be enough if we didn't have these those high CO2 levels that also amplify the warming within the tropics. So it's basically a balance between the extratropical and the tropical warming. When you've got low CO2 levels, so the extratropical warming is going to be more significant than the tropical warming. But with high CO2 levels, this also amplifies the warming within the tropics and causing this imbalance between the tropics and the extratropics.
Okay, thank you.
Contrasting.
Yeah. Any other questions from the audience? You can just speak up if you like. So I have another question. So do you see the weakening of Walker circulation in the mid-Pliocene as well?
Yeah, so related to the Walker circulation, we do not have a clear response of the PMIP models. So the response is clearer for the Western Pacific, but not for the entire Walker circulation in the mid-Pliocene.
Okay.
So that's why the response of the winds in the Western Pacific it ends up being more important than the entire Walker circulation.
Yeah. Thanks.
Can I comment?
Yes.
Yes.
Please.
Okay. Thank you very much for your very interesting talk. To distinguish between the CO2 effect and other effect for the polar amplification and also for your ENSO, I think you can use an extra additional experiments that the PLMIP people did because they did additional experiment to distinguish between the CO2 forcing and the non-CO2 forcing. So would you like to try to look at those multimodals and plot them? The non-CO2 forcing versus the CO2 forcing experiment?
Yeah, I think that would be great. I think it's a very important question. At the time that we were starting or analyzing the PLIOMIP data, those sensitivity simulations of the PLIOMIP were not available for most of the models. So some of the models were still working on getting those simulations. So yes, and hopefully for the PLIOMIP 3, we can expect it to have some more modeling groups join the PLIOMIP and doing some more sensitivity experiments, which are very important for distinguish the drivers between those different forces. But yeah, definitely that would be very interesting to have a look at those sensitivity experiments of the Pleistocene.
Yeah. For PLIMIP 2, it's already available, so I think it will be nice to see it. Thank you very much.
Thank you, Ayako.
Yes. Do you have you looked at any consistency with proxy records or any possibility of doing such studies?
Yeah, so the proxy records, it's a very interesting question. But we have one issue of the with proxy records is the temporal resolution as we go further back in time, and it's much more difficult to distinguish between the changes in ENSO variability. But we do have some proxy records for the mid-Holocene. And for the mid-Holocene, they indicate an increase in ENSO activity from the mid to the late Holocene. And this was also accompanied by a southward shift of the ITCZ. So that's very clear, for example, from the Cariaco Basin records, we can clearly see a southward shift of the ITCZ. And it seems to be in agreement with what the PMIP models are telling us.
Yeah, maybe it's difficult to compare to the ENSO amplitude, but maybe you can check with the mean state of the structure of the SST and such variables, I thought.
Definitely.
Yeah, thank you very much. So I would like to thank you, Gabriel. I would like to move to next speaker, Yasuto Watanabe, who is,
Hi.
Who is the research associate at the Meteorological Research Institute of Japan Meteorological Agency. He talks about drivers of the 41 kilo-year glacial cycles during the early Pleistocene. Please just please
thank
start.
you for introduction. And this is Yasuto Watanabe from Meteorological Research Institution. And thank you very much for this opportunity. So before I start my talk, I briefly introduce myself. I'm Yasuto Watanabe from Meteorological Research Institute in Japan, and I got my PhD from the University of Tokyo 2 years ago. And my research interest covers a broad range of the topic of the modeling of the Earth system, and actually the topic of my PhD was much different from the interest of the PMIP community. And actually, that's about the evolution of the atmosphere on our Earth, like 2 or 3 billion years ago, like a great oxidation event. But I've also been long interested in the quaternary climate change, and which is the main topic of today's talk. I'm going to talk about the drivers of the 41 kilo-year glacial cycles during the early Pleistocene. This research was done when I was in the Atmosphere Ocean Research Institute in the University of Tokyo, working with Professor Ayako Abe-Oji and these other people. So the climate change in the quaternary is characterized by the glacial and interglacial climate cycles, which is recorded in paleoclimate proxies like this. This climate change will be caused by the variations of the northern hemisphere ice sheets driven by the variations of the astronomical forcing. However, the characteristics of the glacial cycles during the early Pleistocene seems to be different from the late Pleistocene period. The dominant periodicity of the cycle is around 41 kilo-year around here, and while it has shifted to 100 kilo-year during the late Pleistocene. The amplitude of the cycle is also small in the early Pleistocene, and it has increased during the middle Pleistocene, and the shapes of the glacial cycle is more asymmetric in the late Pleistocene, characterized by the famous sawtooth patterns like this. So recently, CO2 reconstructions of the early Pleistocene infer that the atmospheric CO2 level during the early Pleistocene would have varied within the similar range to the 100 kiloyear world in the late Pleistocene. This highlights the importance of the response of the Northern Hemisphere ice sheet to the astronomical forcing during the early Pleistocene to form 41 kiloyear glacial cycles. For this purpose, we have further focused on the period shown in blue hatched area here, where clear and continuous 41 kiloyear cycles are observed on paleoclimate proxies. So this is a close look of the delta 18 proxies from MIS53 to 36 here. And because the periodicity of the 41 kiloyear glacial cycles is almost the same with the variations of obliquity of the Earth, these two curves are often compared. And also the variation of obliquity is almost symmetric. The glacial cycle exhibits some patterns in its shape. For example, the interglacial at MIS49, sorry, I forgot to put the numbers, but MIS49, 47, and here for 37 are long, and the glaciations tends to occur in short time interval around here. And while the glaciation from MIS43 to 42 looks so fast. These characteristics in shape of the glacial cycle indicate that the 41 kiloyear cycles are not a simple response to the obliquity forcing. Indeed, recent studies infer the importance of the precession forcing in driving the glacial interglacial transitions during the early Pleistocene. However, the physical mechanisms which determines the length of the interglacials and the timing of the terminations during the early Pleistocene have not been clearly demonstrated. So here, our purpose is to simulate the 41 kiloyear glacial cycles during the early Pleistocene using the three-dimensional ice sheet model coupled to climate parameterization to reveal the cause of the different lengths of interglacial, the mechanism that drives the termination of the 41 kiloyear glacial cycles, and the combined role of obliquity and climatic precession. For this purpose, we use the ACEAS model, which couples the dynamic three-dimensional ice sheet model and climate parameterization. The parameterization was created based on many simulations of the Myrock system coupled with the dynamical vegetation model, taking into account of the climatic effect of the changes in the astronomical forcing and atmospheric CO2 level. In this study, we have improved the climate parameterization by introducing the effect of obliquity on the shift of the surface vegetation of boreal forest and tundra at higher altitudes, which increases the surface temperature when obliquity is high. As a result, the input of the model, Myrock model, are the variations of the orbital astronomical forcing and the atmospheric CO2 concentration, which are given to the model. And first, with these climate forcings, the dynamical evolution of the Northern Hemisphere ice sheets are simulated. Using this model, we simulate the 41 kiloyear glacial cycles from MIS53 to MIS36. So first, we run our model using a combination of realistic variations of astronomical forcings and a constant CO2 forcing, which is fixed at 230 ppm to isolate the role of astronomical forcing. The time series of the simulated ice volume is shown here, and even with the constant CO2 forcing, clear and continuous 41 kiloyear glacial cycles from MIS53 to 36 are simulated in our model. This result indicates that the response of the ice sheet dynamics to the variations of astronomical forcing in the Northern Hemisphere would primarily drive the 41 kiloyear glacial cycles during this period. The result shows that the timing of each deglaciation and the shapes of each glacial cycle are very similar to the delta 18 signatures. For example, the length of the interglacial periods differs from the long patterns at MIS-46 and 9, 47, and 37 to the short one at MIS-41, which is consistent with the Laurentine proxies. In addition, this result shows that the simulated degradation occurs with a relatively short intervals, less than around 15 kilo-year. This is also consistent with the observed trend. And in addition, the first glaciation from MIS-43 to 42 has also been simulated in the model. And we further conducted the simulations using non-constant CO2 input. The result with this non-constant CO2 forcing, shown with red and blue colors, exhibit little differences from the result with constant CO2 in terms of the shapes and amplitudes of the glacial cycles. The timing of the degradation and the dominance of the 41 kilo-year periodicity are almost identical to the standard constant CO2 case. So it could be inferred that the establishment of the 41 kilo-year periodicity and shapes and amplitudes of the variations of the glacial cycles during this period was determined primarily by the variations of astronomical forcing. For this reason, we continue to analyze the model results with the constant CO2 at 230 ppm to understand the fundamental role of astronomical forcing. And as we have seen in the previous slide, our model estimates that the variations of the astronomical forcing cause the sea level change of around 60 to 100 meters during the glacial and interglacial period, between the glacial and interglacial periods in the early Pleistocene. And as seen in the spectrum and a black line in this figure, the periodicity of the obliquity showed a strong signal. However, the actual periodicity of obliquity showed a strong signal. However, the actual sea level change is also affected by the variations of the Antarctic ice sheet. It has been hypothesized that because the signal of precession and the insolation forcing is antiphased in the southern hemisphere compared with the northern hemisphere, the variations of the Antarctica may cancel the signal of precession from the paleoclimate proxy. To compare our simulation with the reconstructions of the variations of the global mean sea level, we use the variations of the Antarctic ice volume estimated by previous studies. We added the variations of the southern hemisphere ice sheets estimated in previous study to our simulated northern hemisphere ice sheet variations. Despite the non-negligible amplitude of the variations of the Antarctic ice sheet, the amplitude of the sea level variation is almost as large as the one without considering the variations of Antarctica. This means that the variations of the northern hemisphere ice sheet dominates the global sea level change. In any case, the range of the amplitude of the simulated sea level change is broadly consistent with reconstructions. Nevertheless, after considering the Antarctica, the power spectrum exhibits that the variations of the simulated global sea level shows a clear dominance of the 41 kilo-year periodicity, the obliquity forcing, with very small precession signal than that of the northern hemisphere ice volume alone. This is because the 20 kilo-year component of the precession signal is cancelled by the variations of the southern hemisphere ice sheet. And this is consistent with the records of the signal of the reconstructed signal from the paleoclimate proxy. So next, we further focus on the role of the northern hemisphere ice sheets in driving the patterns of the shapes of glacial cycles and the timing of the glaciation. For this purpose, the boundaries of the interglacial and glacial periods are defined in the study as the midpoint of the maximum and minimum ice volume for each deglaciation. Here, the blue and orange area represent the interval of the glacial and interglacial periods defined in this study. So to quantify the contribution of the obliquity and precession forcing in determining the timing of the deglaciation, we conducted a phase analysis at each degradation. And the phase wheel shown here for precision and obliquity. Precision and obliquity is shown here. And this phase wheel summarizes the phase angle of the precision and obliquity at each degradation as the position of the diamond shown here. The average phase angle of both precision and obliquity is represented by the direction of the thick black line, which is around 0 for both obliquity and precision. This means that the degradation mostly occurs at precision minima and obliquity maxima. This results infer that both obliquity and precision forcing pace the degradation of the 41 kiloyear glacial cycles, and which is consistent with the discussion for the 100 kiloyear glacial cycles during the late Pleistocene. However, the phase angle of precision tightly concentrates around 0 degree for all degradation analyzed here, while that of those of obliquity disperse wider, suggesting that precision is crucial in determining the precise timing of degradation, not only in the late Pleistocene, but also in the early Pleistocene. So then we discussed the lengths of the interglacial periods. For this purpose, the phase angle of precision and obliquity as the beginning and end of all simulated interglacials shown with orange areas are summarized here according to typical variations of precision and obliquity signal. This analysis is similar to the research for the interglacial of the late Pleistocene using a paleoclimate proxy conducted by Tsedaki et al. And using for the late Pleistocene. But we did it using a simulated result for the early Pleistocene, as shown here. As we mentioned, the onset of the interglacial occurs at maximum of precision forcing. So the timing of the end of the interglacial periods range from 10 to around 30 kiloyear after the onset. For MS 45, 43, and 41, the interglacial period ends within one precision cycle, while for these and 3 and these 2 interglacials, the interglacial periods continue beyond one precision cycle. Also, you can see that the duration of the interglacial tends to be long if it starts earlier than the obliquity maximum, and whereas it is short when the interglacial starts after the obliquity maximum. In any cases, the end of the interglacial periods occurs around the minima of obliquity and precision forcing. In other words, the length of the interglacial periods is likely to be controlled by the lead-lag relationship between the maximum of obliquity and precision forcings. So here I try to understand this behavior. To understand why the glacial cycles of the Northern Hemisphere ice sheet terminate every 41 kiloyear, we compare the 3 continuous cycles from MS47 to 41, and with the steady state response of an ice sheet to astronomical forcing. The steady state response of an ice sheet to the surface temperature change anomaly due to the insolation and CO2 change is shown here. The cyan and magenta lines represents the steady state achieved if the model is initiated from a small ice sheet condition and large Northern Hemisphere ice sheet conditions. The hysteresis behavior could be observed around here, and the ice sheet gains mass if the temperature anomaly falls below the lower branch of the hysteresis curve written with cyan line, and it loses mass if the temperature anomaly rises above the upper branch written with magenta line. For the typical 41 kiloyear cycle of the sawtooth shape, such as from MS45 to 43, shown in black line, ice sheet retreat occurs once in every 2 precision cycles. As the surface temperature decreases, this ice sheet gains mass. At first insolation maximum after the onset of the glacial cycle, the intensity of insolation is insufficient to exceed the threshold of termination shown with magenta line. This is because the effect of the precession and obliquity forcing cancels out so that the ice sheet continues to develop. At the second local maximum of insulation, on the other hand, the insulation is strong because the contribution from obliquity and precession are compounded. So not only because of the high insulation, there's enough time for the ice sheet to retreat completely. After crossing the upper threshold, the ice sheet starts to lose mass because the insulation during this period is large. This allows the temperature to exceed the threshold and thus triggers the onset of the degradation. So once degradation has commenced, feedback from glacial isostatic rebound assists the complete degradation to the interglacial level. This works to increase the temperature of the ice sheet ablation zone. And so as a result, the degradation occurs once in 2 precession cycles through the threshold mechanism that results from the hysteresis response of the ice sheet as in the late Pleistocene. So for the glacial cycles from -47 to 45 shown with red lines, and the interglacial period is longer than 1 precession cycle here. The ice sheet does not develop at first minimum of the precession forcing, but it does develop rapidly at the second minimum in the precession forcing. In contrast, the interglacial period is short in the case of the cycle from -43 to 41, shown with blue line, and the ice sheet starts to develop soon after the previous degradation at the first minimum in precession forcing, and the glacial period continues for more than 1 precession cycle. In all 3 cases analyzed here, the degradation occurs once in 2 precession cycles through the threshold mechanism of the ice sheet of the northern hemisphere. So this is the reason that the differences between the shapes of the 41 Curie cycle reflects the phase relation between obliquity and precession forcing. So we go back to this figure, but here the blue and red line summarizes the length of glacial and interglacial periods. This result indicates that the lengths of interglacial and glacial periods are inversely correlated. This pattern reflects the phase relation of obliquity and precession forcing at each glacial cycle. So the shapes of glacial cycles during the early Pleistocene could be classified according to the phase relation of the obliquity and precession forcing. When the peak of precession forcing comes later than the obliquity peak, it has a plateau-like interglacial like this. On the other hand, when the peak of precession forcing comes earlier than that of obliquity, it is U-shaped like this. If the peak of obliquity and precession aligns, it is like sawtooth pattern as shown here. So finally, to understand the importance of the astronomical forcing in sustaining the 41 Curie periodicity, we conducted an additional sensitivity test. First, we varied the amplitude of eccentricity, that is the amplitude of the precession forcing, like this one. And we used a set of artificially modified astronomical forcing with smaller amplitude of eccentricity variations. When the amplitude of eccentricity is small, the 100 Curie periodicity of ice volume increases as shown in red lines. For the case with red line, only a few degradations are reproduced in the model. So we have also repeated similar sensitivity tests with respect to the different amplitude of obliquity. And in this case, the 100 Curie periodicity of the glacial cycles has also increased. These sensitivity experiments clearly shows that the combination of the obliquity and precession forcing is important and necessary for sustaining the continuous 41 Curie glacial cycles during this period. In other words, the large amplitude of the obliquity and precession forcing during this period would have helped to achieve the 41 Curie glacial cycles from MS 53 to 36. So, and this is the summary of my presentation. And thank you very much for listening. I take questions.
Thank you very much, Yasuto. I think that the central topic is the changes in ice sheet, but it also has a big implication for the diversity of interglacial period and also a transient nature of interglacial period, which is very relevant to PMIP community. Are there any questions and comments? Or Fabrice has a comment on chat. And anybody has questions?
This research has been published on Communications as Environment last year. So if you have any interest, please check this paper.
So I have a small question that you mentioned that in the beginning that you sort of used new climate, how do I say, new, well, you started your new version of this model setting includes the changes in the vegetation in response to any climatic changes. And so this is a new things. And how important in your overall result that this inclusion of the vegetation, that change, if you exclude the effect of vegetation change, does the what you showed today changes a lot, or how are they important in your sense?
Thank you very much for asking this. And yes, we have conducted 27 calculations using the MIROC atmospheric dynamical circulation model coupled with the vegetation model, as you know. And we showed that the change in the obliquity and is strongly affects the northern hemisphere surface temperature. And so the inclusion of the vegetation works to strengthen the variations of the effect of the obliquity forcing. So the inclusion of the vegetation feedback would help the degradation at each 41 kilo year. So without vegetation feedback, some of the degradation during this period has not been reproduced in the model. So we expect that the changes in the vegetation at the high latitudes of the Eurasia and North America would be important in driving the variations of the ice sheet during the early Pleistocene. The change in the vegetation affects the climate by primarily changing the surface albedo, because the boreal forest has a low surface albedo because it is forest, and the tundra has a relatively high albedo. So yeah, that would be important even in the early Pleistocene.
So I think it's interesting that the sum of that degradation can be missing if you don't include the vegetation, which means that you may have a longer duration of the interglacial period. I think quite important point. So any questions or comment or? Okay. So the surprisingly, as Fabrice commented in chat, surprisingly that this model simulate what we observed in the records very well. So it may not be very important to consider the model dependency, but I'm wondering, because the PMIP community has sort of GCM multimodal comparisons and analysis and stuff like that. And I'm wondering if any sort of the difference in GCMs, something that you can learn from the PMIP, sort of you can sort of interact with your study, or otherwise you can sort of your result can give some feedback to the PMIP GCM simulations. This kind of simulation may be useful for your study, or any aspect will be fine. But if you have any comment on such.
For this, the early Pleistocene period, the model for the Klimba model has also simulated the transient response of the ice sheet and climate system. And it has also successfully simulated the Fourier kiloyear glacial cycles during this period. And yes, the results seems consistent with the other modeling groups, but we have focused primarily on the roles of the astronomical forcing by focusing this period where the 41 kiloyear glacial cycles are observed. And the another important point is that whether it is necessary to use a different boundary conditions like the condition of the surface of the northern hemisphere land to simulate the different periodicity before and during the early Pleistocene and late Pleistocene, and that has a different periodicity of the glacial cycles. So, and the previous study simulated 41 kiloyear glacial cycles using the boundary conditions, assuming the existence of the old thick regolith layer on the surface. And it's okay, but we have simulated the different response using the same boundary conditions, at least for this period and last for 100 kiloyear glacial cycles. So the future important point for future research will be the consideration of the boundary condition in the surface. And another important thing is that the coupling of the sea level change and ice sheet variations to the change in the CO2, and the carbon cycle in the southern hemisphere. So coupled climate, ice sheet, and carbon cycle modeling would be very fruitful topic for future research, I think.
Thank you. So we have a lot for the space for modeling community to further develop and study, I think. Okay, I think it's about time that it's about 1 hour that since we started. So I would like to officially close the PMIP Wings for today. But if any of you wants to chat or continue discussion, that will be fine. I will keep the Zoom open for a while, but I will stop the recording that will be shared with the PMIP community for the people who couldn't participate in a real time. And thank you very much for speakers and participants of the audience. And so I will close now. Thank you. Thank you, Esther and Gabriel.
Thank you
Very much.